about the warm clouds. Okay, the formation and growth of water droplets in the warm clouds. Okay, for the last 7 8 lectures we have been discussing about that only. All right, and in yesterday's class we discussed about the role of giant cloud condensation nuclei uh, in the growth of the water droplets. Actually, such giant cloud condensation nuclei, they accelerate the growth, right? If such kind of giant condensation nuclei were not present in the atmosphere, then wouldn't have got the rainfall that we see, the raindrops that we observe. That kind of raindrops we wouldn't have seen if such giant nuclei were not present in the atmosphere. Okay, they help not only in the growth of the size of the droplets, but also accelerate the rapid formation of such droplets. Okay. Similarly, the turbulence which are present inside the cloud, okay, that also help in the growth process. Also, the radiative heating, okay, the radiative heating also helps in the growth of the water droplets inside the clouds. Okay, uh, in addition to the formation or after the formation because of the condensation and coalescence, right? So these processes exist in the real atmosphere, which help in uh, accelerating the formation of the droplets. Also, the stochastic collection helps in the process. So, so far, so we have been discussing about the growth of the water droplets because of the collision coalescence, right? As the droplets fall through different terminal velocities depending upon the size and mass of the water droplets. Now, sometimes they can collide and sometimes they can also rather get deflected. Instead of colliding, they can also get deflected away, and then in that case, they will not grow. Okay, so only after they collide and also merge or coalesce with the larger droplets, the droplets will not grow. So after all these things have happened and the droplets have grown inside and almost become like a raindrop and started falling down, but once that starts happening, the droplets can also break up. Okay, the larger droplets can also break up while it is falling down. It can also break up. Okay, and produce a wide spectrum of the sizes of the raindrops. Okay, you see that when rainfall is taking place, we have got raindrops of various sizes. Okay, so by all these processes which we have discussed so far in the last 7 8 lectures, we discuss about how the droplets grow in size by various processes, various physical processes: condensation, coalescence, okay, accretion, collision, okay, by the presence of the cloud condensation nuclei, by the presence of the turbulence, radiative heating, okay, and also electrical fields. But once the droplets grow sufficiently large in size and then transform into raindrops and start falling down, they can also break up. Okay, they can also break up. The large droplets or large raindrops can also break up, and produce smaller droplets again of different sizes. Right. So today we are going to discuss about this breaking up processes of the droplets. Right. So raindrops in free fall are often depicted as. Sorry, sorry, we have to wait for a while. Just one. Yeah, I'm sorry about that. Are you able to hear me now? Am I audible and visible to you? Am I audible and visible to you?
Yes, sir.
Okay. So what we're discussing is that the raindrops in free fall are often depicted as tear, the human tear, tear from the eyes. So they are often depicted as tear shaped. Okay. In fact, as a drop increases in size above about 1 millimeter in radius, it becomes flattened on its underside in free fall. And that is also because one of the reasons for that is because it experiences the pressure from the air below the water droplets. Okay, and it gradually changes in shape from essentially spherical to increasingly parachute or like a jellyfish. Okay, they change in shape like a parachute or jellyfish, right? So if the initial radius of the drop exceeds about 2.5 millimeter, the parachute becomes a large inverted bag, okay, with a toroidal ring of water around its lower rim. Right? Laboratory and theoretical studies indicate that when the drop bag bursts to produce a fine spray of droplets, the toroidal ring breaks up into a number of large drops. Okay, this is what is observed or found from the laboratory experiments. Okay, interestingly, the largest drops ever observed at diameter of 0.8 to 1 centimeter. Just imagine that is a very big drop size. 1 centimeter drop size is very big, and such drops cannot sustain. They have to break up. They will break up. Must have been on the verge of bag breakup. Okay. Collisions between raindrops also appears to be more important path to breakup. See, collision acts in two ways. In the initial phase, when the droplets are smaller in size, then the collision between droplets will lead to the growth in size of the droplet because they merge, right? They merge or they coalesce with each other. But when they become large in size, then the same collision can lead to the breakup also. Okay. So the collisions between raindrops appear to be a more important path to breakup. The three main types of breakup following a collisions are shown schematically in this diagram. You see this diagram, it shows three different ways of the drop breakup, the raindrop breakup. Is this diagram visible to all of you? Is this diagram visible to all of you? Yes or no?
Yes,
Yes, sir.
sir.
Okay, okay.
Yes, sir.
So you see, now these are the different shapes of the raindrops. Okay, different shapes of the raindrops when they have increased sufficiently large in size. Its size could be about 0.8 to 1 centimeter. Okay, and they sometimes they look like the tear from the eye. And also their base is flattened. Okay, the base is sometimes flattened. The shape changes from a spherical shape to a flattened base type of shape. Okay, so once they are falling down, they can also collide and then the breakup. So there are three ways or three types depicted in this figure. One is the so-called sheet breakup, other is called the neck breakup, and third is the disc breakup. Okay, the raindrops are now breaking up. Initially, the raindrop formed because of the collisions and collisions. Okay, by stripping of the smaller droplets by the larger droplets, and once they have become large in size and started falling down, then they started also breaking up. Okay, however, individual drops have to reach very large sizes before they break up. Okay, also the frequency of collisions between raindrops is very small except in very heavy rain, right? Unless the rainfall intensity is very heavy, that means the rate. Now, how many millimeter per hour? Say 10 millimeter per hour, we say quite a good intensity of rainfall. So, unless the intensity is very large, and also the size of the raindrops are also sufficiently large, okay, the breaking up does not occur. Okay, So the frequency of collisions between raindrops is very small except in very heavy rainfall. For example, a drop with a radius of 1.7 millimeter in rain of 5 millimeter per hour would experience only one collision as it falls to the ground from a cloud base at 2 kilometers above the ground. Okay, cloud base is 2 kilometers above the ground. Okay, the rainfall intensity is 5 millimeter per hour, and the radius of the raindrop is a 1.7 millimeter. In such situation, the rainfall or the raindrops will experience only one collision, and this is what is observed from the laboratory studies. This is observed from the laboratory studies that the typical radius at 1.7 millimeter, rainfall intensity of 5 millimeter per hour, okay, would have only one collisions as it falls toward the ground. Okay. Theoretical predictions of the probability of breakup as a function of the sizes of two coalescing drops are shown in the next figure 21. Okay. This diagram is showing you the radius of large drops versus the radius of small drops when they are falling down, and the probability of the collision. These contours that you are seeing indicate the probability of the collision, right? So as you can see from this diagram, suppose for a larger raindrop of suppose say 0.1 centimeter radius, okay, if it is colliding with a smaller droplet of say 0.01, okay, radius, centimeter radius, then the probability of the breaking, okay, the probability of breaking is very less, about 0.3. Okay, that means about 3%. Okay, 3%. So as the raindrops are increasing in size, suppose at a fixed radius of the large drop, let us say at 0.1 centimeter, as this radius of the smaller drops are increasing from 0.01 to 0.02, 0.05, okay, then the probability of the raindrops breaking up is also increasing. Say is increasing from 0.3 to 0.4 to 0.5 and so on. Okay, but after reaching a critical value, then they again start their probability starts decreasing. Okay, so this is what is depicted in the diagram. Just I have to take a break for a few minutes. Okay, I'll be just back. Yeah, I'm sorry for the interruption. So, are you all there? I see 8 people are there. Okay. So, am I audible and visible?
Yes, sir.
Yeah. Okay. Good. Yeah. So, we're discussing about the probability of the raindrop breakup. Okay. When two droplets of different sizes they collide with each other while falling down to the ground. Okay. And we were saying that initially, suppose for a given size of the large raindrop, let us say at 1 centimeter or zero point 0.2 centimeter, and this is the smaller drop sizes of different radius like 0.01, 0.02, and so on up to 0.2 centimeter. So initially, the probability of the breakup is small because this size of the smaller droplets is very small. But as the size increases, the probability also increases from 0.3 to 0.4 to 0.5 and so on. Okay, but after reaching the maximum, again they start decreasing. Okay, so this is the probability of raindrop breaking. Now this figure shows the empirical results for probability of breakups, okay, as studied from the laboratory experiments, expressed as a fraction and shown on the contours. They are the contours of the probability, okay, contours of the probability following the collision and initial collisions of the two drops, right? For a fixed size of larger drop, the probability of breakup initially increases, as I said, I explained to you earlier, as the size of the smaller drop increases, but as the smaller drop approaches the size of the large drop, when the two drops become almost equal in size or similar in size, okay, the probability of breakup decreases due to the decrease in the kinetic energy of the impact. Okay, measurements of the size distribution of raindrops that reach the ground can often be fitted to an expression known as the Marshall-Palmer distribution. Okay, this is a very standard relation, Marshall-Palmer distribution, which provides us the size distribution of raindrops. Sometimes, in calculation or modeling of the cloud microphysical parameters, many times we have to uh, uh, estimate the size distribution of the water droplets inside the clouds. And since this is at a very micro level taking place, so modeling such processes are quite complex. Right. So instead of going into details of the calculation of the size distribution, many times we assume a simple relation of the water droplet distribution based upon the so-called Marshall-Palmer distribution, okay, which is of the form this one, n function of d equal to n0 exponential of minus hat d, okay, where n is the number concentration of the droplets, okay, which is a function of the diameter, okay, and this one, NDDD, is number of the drops per unit volume with diameters between D and D plus DD. And N0 are the empirical fitting parameters. All these N0 and this hat, inverted hat, are all the empirical fitting parameters. So this equation number 14 is the standard form of the Marshall-Palmer distribution. Okay, Marshall-Palmer distribution, which we use to estimate the size distribution of the raindrops or the cloud droplets while modeling it, okay, in the NWP models, Marshall-Palmer distribution. The value of N0 tends to be constant but varies with the rainfall rate. Okay, this N0 will vary with the rainfall rate. All right. So this is all about the warm cloud. Okay, the growth, the development and growth of the water droplets inside the warm clouds. Okay, and we had discussed in the beginning of this class, earlier, that warm clouds are those whose tops are generally below the freezing level, right? So the other category of clouds is the so-called cold clouds, right? Cold clouds, right? And the cold clouds have their tops generally above the freezing level, in the sense that, freezing level, that means the level where the temperature is 0 degrees centigrade or the 0 degree isotherm. Okay, that is the freezing level. So the clouds whose tops are above the freezing level, they are generally called the cold clouds, in which we generally find the ice crystals. Okay, and so now we shall discuss about the growth of the ice crystals, how the ice crystals grow inside the cold cloud. This is what we are going to discuss in the next few classes. Okay, in the next few classes, we are going to discuss about the formation and growth of the ice particles in the cold clouds. Okay, so also we have discussed in 7-8 lectures about the warm clouds. Now we are going to discuss about the cold clouds. All right, is everybody listening to me carefully?
Yes, sir.
Okay, good, very good. So now let's talk about the microphysics of the cold clouds. All right. If a cloud extends above the 0 degree centigrade level, it is called a cold cloud. Okay, that is the isotherm, 0 degree isotherm. Even though the temperature may be below 0 degrees centigrade, water droplets can still exist in the clouds. It is not necessary that once the temperature is 0, the water droplets will freeze immediately. Not necessary. Okay, they can still exist in the form of water. They may not immediately form into ice, or they may not immediately freeze into ice particles. Okay, actually, studies have shown that the water droplets can exist in the liquid form at temperatures as low as minus 40 degrees centigrade. Just imagine. Okay, the water droplets can exist in the form of liquid, or the cloud droplets can exist in the form of liquid at temperatures as low as minus 40 degrees centigrade. But beyond that, if it falls, if the temperature drops beyond that, there is a spontaneous nucleation. There is a spontaneous nucleation. That means the super cool, the water droplets at such a low temperature are generally called the super cooled water droplets. Super cooled water droplets. So if the temperature falls further beyond minus 40 degrees centigrade, then generally there is a spontaneous nucleation. Immediately that will turn into ice crystal. Okay, but that is in a clean air. That is the situation. That is the case in a very clean air in which there is no foreign particles. There is no aerosol. Air is clean. The water droplet or the cloud water droplet is very, very pure. Then only that situation occurs. But generally in real atmosphere, that is not the case. Okay, in real atmosphere, we know that there are so many types of aerosols present. Okay, and some of these aerosols act as a ice nuclei, just like we discussed in the warm cloud, the condensation nuclei. The condensation nuclei like Aitken nuclei, large nuclei, giant nuclei. We discussed about that for the warm clouds, which act as a platform for the condensation of water vapor. Right. Similarly, in the cold clouds, there are many types of aerosols which act as a ice nuclei for the formation of the ice crystals. Okay, so water droplets can still exist in clouds, in which case they are referred to as the supercooled droplets. Okay, cold clouds may also contain ice particles. Okay, it can have a mixed phase also. Mixed, that means the cloud whose tops are rising above the 0 degrees centigrade isotherm have both mixture of the liquid water droplets as well as the ice particles. Okay, if a cold cloud contains both ice particles and the supercooled droplets, it is said to be a mixed cloud. Okay, if it consists entirely of ice, it is said to be glaciated. Okay, when the cloud consists of entirely ice particles, ice crystals, that is called glaciated. But when they got both the form, okay, both the phase of the water, like it has super cooled water droplets as well as the ice crystals, then it is a mixed cloud. Okay, we shall discuss about the origins and concentrations of the ice particles in the clouds, the various ways in which ice particles can grow, okay, and the formation of precipitation in the cold clouds. All right. So now let's talk about the nucleation of ice particles in the ice nuclei or the ice nuclei. Okay, just like the condensation nuclei which we had discussed earlier, we are going to discuss now the ice nuclei. All right. For freezing to occur, enough water molecules must come together within the droplet to form a embryo of ice large enough to survive and grow, just like the embryos of the water droplets in the warm clouds which form by the condensation from the water vapor. Similarly, in the cold clouds, enough water molecules must come together within the droplet to form an embryo of ice large enough to survive and grow. The situation is analogous to the formation of water droplet from vapor phase discussed earlier. Right? If an ice embryo within a droplet exceeds a certain critical size, its growth will produce a decrease in the energy of the system. Okay. However, any increase in the size of an ice embryo smaller than the critical size causes an increase in the total energy. Okay. So in the latter case, from an energetic point of view, it is preferable for the embryo to break up. Okay. To break up. If a water droplet contains no foreign particles, it is pure, it can freeze only by homogeneous nucleation. Okay, just like in case of the warm cloud, we have got homogeneous and heterogeneous formation of the water droplets. Similarly, in the case of cold clouds also, if there is an absence of any foreign particles, then it can freeze only by the homogeneous nucleation. Everything is in the form of pure water. Okay. Because the numbers and sizes of the ice embryos that form by chance segregation increases with decreasing temperature below a certain temperature, which depends on the volume of water condensed considered, freezing by homogeneous nucleation becomes a virtual certainty. Okay. Freezing by the homogeneous nucleation becomes a virtual certainty. The results of laboratory experiments on the freezing of very pure water droplets, which were probably nucleated homogeneously, are shown in the next figure, 21. Okay. This figure is illustrating the median freezing temperature. Okay, on the y-axis, the median freezing temperature from -50, -45, -40, and so on, -15 degrees centigrade. And on the x-axis, we have got the equivalent drop diameter: 1 micron, 10 micron, 100 micron, 1 millimeter, 1 centimeter. Okay, and then the median freezing temperature for different equivalent drop size is shown here by the blue and the red curves. Blue and the red curves. Okay. So this diagram is showing the median freezing temperature of the water samples as a function of their equivalent water drop diameters. The different symbols are results from different workers. Okay. I mean, different authors have found different results, but they're all matching and falling into the same line. Although these small plots on the graph are scattered, but they're almost like on the same line, both for the red as well as the blue curve. The red symbols and the red line represent the heterogeneous freezing. Okay, this is representing the heterogeneous freezing, and the blue symbols and the blue line represent the homogeneous freezing. Okay, so as you can see from these curves, the rate of growth of ice particles inside the cloud is very rapid. Okay, very rapid in the heterogeneous nucleation. That means when there is the presence of foreign particles, the heterogeneous nucleation takes place, and that results in very rapid growth of the ice crystals. Whereas in case of the homogeneous nucleation, the rate of growth is not so fast, okay, as compared to the heterogeneous nucleation, right? We shall talk about how different ice nuclei behave in different ways, okay, and which is the best ice nuclei conducive for the growth of the ice crystals inside the cloud, okay. Results show that homogeneous nucleation occurs at about minus 41 degrees centigrade. I was telling you earlier that pure water can exist in supercooled state even as low temperature as minus 40 or minus 41 degrees centigrade. Okay, for droplets of about 1 micron size. Okay, in diameter, and at about minus 35 degrees centigrade for drops of 100 micron in diameter. So this existence of this supercooled state of the pure water droplets also depends on the size, right? Like larger size water droplets can remain in the liquid form at temperatures up to minus 35 degrees centigrade, whereas smaller droplets of size 1 micron can remain in the liquid phase at temperature up to minus 41 degrees centigrade. Okay. Hence, in the atmosphere, homogeneous nucleation of freezing generally occurs only in high clouds, okay, like cirrus cloud, cirrocumulus cloud, cirrostratus cloud. Only in such high clouds where the air is pure, okay, the water is highly supercooled, okay, and in the pure form, only in such high clouds the homogeneous nucleation can occur, okay, right? Whereas the ice crystal can also occur in the clouds at lower altitude, right? Generally, cirrus clouds, as we have discussed in the beginning, cirrus clouds are high clouds and whose bases are about 6 to 7 kilometers. Okay, but in such high clouds of cirrostratus or cirrocumulus, etc., or cirrus, the homogeneous nucleation of ice crystals can occur, whereas ice crystals which occur inside the clouds below 6 to 7 kilometer base can occur due to the heterogeneous nucleation also. Okay. 11. Okay. So if a water droplet contains no foreign particles, it can freeze only by homogeneous nucleation. We have already discussed about this. Because the number and sizes of ice embryos that form by chance aggregation increases with increasing temperature. Below certain temperature, which depends on the volume of water considered, freezing by homogeneous nucleation becomes virtual certainty. I think we already discussed about this. Okay, this is we have discussed. Yeah. A droplet contains a rather special type of particle called a freezing nucleus. It may freeze by a process known as heterogeneous nucleation, okay, in which water molecules in the droplet collect onto the surface of the particle to form an ice-like structure that may increase in size and cause droplets to freeze. Okay, because the formation of the ice structure is aided by the freezing nucleus, and the ice embryo also starts off with the dimension of the freezing nucleus, heterogeneous nucleation can occur at much higher temperatures than the homogeneous nucleation. As we discussed earlier, for homogeneous nucleation to occur, the clouds have to be very high, like cirrus cloud, right? Whereas the heterogeneous nucleation can occur even at lower altitude and at lower temperature, right? The same diagram is getting repeated here. Now, in this diagram, the droplet consists of distilled water from which most but not all of the foreign particles were removed. Okay, this laboratory experiments which was conducted now had distilled water, that is pure water from which most but not all the foreign particles were removed. Okay, a large number of droplets of each of the sizes shown in this figure were cooled, and the temperature at which half of the droplets had frozen was noted. How the experiment was conducted. Okay, it can be seen that this median freezing temperature increases. Okay, as the size of the droplet increases. Okay, the freezing temperature increases for a larger size. For example, for 10 micron size or 100 micron size, the median freezing temperature is also increasing from -40 to -35 to -30 and so on. Okay, the size dependence reflects the fact that a larger drop is more likely to contain a freezing nucleus capable of causing heterogeneous nucleation at a given temperature. Okay. We have assumed earlier that the particles that initiate the freezing is contained within the droplets. Okay, the nucleus or the ice nuclei are contained within the droplets. However, cloud droplets may also be frozen if a suitable particle in the air comes into contact with the droplet, in which case freezing is said to occur by contact nucleation. Okay, in that case, freezing occurs because of the contact nucleation, and the particle is referred to as the contact nucleus. Okay, contact nucleus. Laboratory experiments suggest that some particles can cause a drop to freeze by contact nucleation at temperatures several degrees higher than if they were embedded in the drop. Okay, so see the difference. One is the type of nucleus which is embedded within the drop, inside the drop, and other one is the contact nucleation, in which case supercooled water droplets come into contact with the surfaces of the foreign particles, or so-called the ice nuclei. Okay, two different types. So when they come into contact with the foreign particles, the nucleation is faster than compared to when it is contained within or embedded within the drop. Certain particles in the air also serve as centers upon which ice can form directly from the vapor phase. Okay, ice can form directly. You know the sublimation process I have studied in the thermodynamics, the sublimation, right? In which case, ice can form directly from the water vapor. Okay, these particles are referred to as deposition nuclei. Okay, when the ice particles form inside the clouds by sublimation process, then they are called the deposition nuclei. Okay, deposition nuclei. That means the water vapor is coming into contact with such ice nuclei where it immediately freezes, and it's called the deposition of the nuclei. Deposition nuclei. Okay, ice can form by deposition provided that the air is supersaturated with respect to ice and the temperature is low enough. Okay, supersaturation has to exist for the deposition to occur. Okay, if the air is supersaturated with respect to water, a suitable particle may serve either as a freezing nucleus or as a deposition nucleus. Okay, so see the two different types. One is a freezing nucleus, other is the deposition nucleus. Okay, and you see the difference between the two. Like in case of freezing nucleus, the supercooled water droplets which is coming into contact with such nuclei are turning into ice or freezing. Okay, so that means from liquid it is freezing to solid, right? Whereas in case of depositional nuclei, even the water vapor which comes into contact with such nuclei immediately transform into the solid phase. So this is called the deposition of the ice, and such nuclei are called the deposition nuclei. Right? So if we wish to refer to an ice nucleating particle in general, without specifying its mode of action, we will call it an ice nuclei. I mean, ice nucleus is a generalized term used for all kinds of nuclei which acts to or which helps in formation of the ice particles. However, it should be kept in mind that the temperature at which a particle can cause ice to form depends in general on the mechanism by which the particle nucleates the ice, as well as on the previous history of the particle. Okay. Particles with molecular spacings and crystallographic arrangements similar to those of the ice, which has a hexagonal structure, tend to be effective as ice nuclei. Okay. Although this is neither necessary nor a sufficient condition for a good ice nucleus. Okay. So what it is saying is that the substances or the nuclei whose molecular structure is similar to that of the ice tend to be a effective ice nuclei. Okay. So in order to act as a ice nuclei, a foreign substance should have its molecular spacings and structures like an ice particle. Most effective ice nuclei are virtually insoluble in water. Okay. Some inorganic soil particles, mainly clays, can nucleate ice at fairly high temperature, that is above minus 15 degrees centigrade, and probably play an important role in nucleating ice clouds. Okay. Many organic materials are effective ice nucleators. Decayed plant, for example, decayed plant leaves contain copious ice nuclei, some active as high as minus 4 degrees centigrade. Right? These are the organic materials. Decayed plant leaves can act as a active nuclei and can freeze the water droplets even at temperature as high as minus 4 degrees centigrade. Okay, ice nuclei active at minus 4 degrees centigrade have also been found in seawater rich in plankton. Okay, in seawater also we find active ice nuclei. All right. The results of laboratory measurements on the condensation, freezing, and deposition are shown in this figure 22, okay, which shows temperature versus the ice supersaturation. Okay, in y-axis we have got the ice supersaturation in terms of percentage. Okay, 5% above the saturation, 10% above the saturation, and so on. 30% above the supersaturation. I mean, above the saturation, that is supersaturation, right? For different temperatures, minus 5, minus 10, and so on, minus 25 degrees centigrade. Okay, and this line is showing how the presence or different types of ice nucleus plays a role in formation of the ice particles depending upon what is the temperature and what is the supersaturation with respect to the ice. Okay, so accordingly, for certain temperature and for the certain supersaturation, there can be condensation, freezing, there can be deposition or water saturation. Okay. This figure shows the onset of the ice nucleation as a function of the temperature and supersaturation for various compounds. Okay. You can see, I don't know whether you will be able to, are you able to see the difference in the colors for these lines? Are you able to see the colors of this line? Can you see the colors?
Yes, sir.
Yeah.
Yes, sir.
Some are red, yeah, some are red, some are blue, some are green. Okay. So these different colors are indicating the different organic substances. Okay. The onset of ice nucleation as a function of the temperature and supersaturation for various compounds. Okay. Conditions for condensation, freezing, and ice deposition are indicated ice nucleation starts above the indicated line. Okay, this is the line, indicated line. So above this line, the ice nucleation starts. The materials are silver iodide. The red curve is for the silver iodide. The blue curve is for the lead iodide, and the violet curve is for the methyldehyde. Okay, and the green curve is for the kaolinite. Okay, so different compounds. Okay, different organic compounds like kaolinite. Okay, some sort of a clay, methyldehyde, lead iodide, and silver iodide. Okay, these are different organic materials which are sometimes used also in the cloud seeding experiments, in freezing the water droplets quickly or more rapidly, right, in the clouds. Okay. Now, the last figure indicate that for a variety of materials, the onset of ice nucleation occurs at higher temperatures under water supersaturation supersaturated conditions, so that condensation freezing is possible than under water saturated conditions when only ice deposition is possible. Okay, as you saw in the previous diagram, okay, as you saw in this diagram, now one side is the deposition, other side is the condensation freezing. Okay, and that depends upon the materials, the organic compound. Okay, and also depends upon the supersaturation with respect to ice present in the cloud. Okay, and temperature. Okay, so this indicates a variety of materials. The onset of the ice nucleation occurs at higher temperatures under water supersaturated conditions, so that condensation freezing is possible than under water subsaturated conditions when only ice deposition is possible. For example, the kaolinite serves as an ice nuclei at temperature minus 10.5 degrees centigrade at water saturation, but at 17% supersaturation with respect to ice, but subsaturation with respect to water. Okay, it is saturated with respect to ice or supersaturated with respect to ice, but subsaturated with respect to water at minus 10.5 degrees centigrade. Okay, the temperature has to be about minus 20 degrees centigrade for kaolinite to act as an ice nuclei. Essentially, so what it says is that now, depending upon the organic compound or organic material present in the atmosphere, and also the supersaturation, whether it is with respect to water or whether supersaturation is with respect to ice. Okay, for different temperatures, it can act as a ice nuclei. Okay, in some cases, after the particle has served as an ice nucleus, and all of the visible ice is then evaporated from it, but the particle is not formed above minus 5 degrees centigrade or exposed to a relative humidity with respect to ice of less than 35%, it may subsequently serve as an ice nucleus at a temperature a few degrees higher than it did initially. And this is referred to as the pre-activation. Pre-activation, just like in the case of warm cloud. Now we discuss about the droplet is activated, right? The droplet, water droplet is activated inside the cloud, or we discuss it is inactivated. Similarly, in case of the ice cloud or the cold cloud also, some nuclei which now in the beginning served to nucleate the ice at a relatively lower temperature, it will act as a nuclei now at a faster rate, now say 35% or ice of less than 35%, now which subsequently serve as an ice nucleus. Okay, at a temperature few degrees higher than it did initially. Okay, so this is referred to as a pre-activation. The Hello? Are you all there?
Yes, sir.
Sorry, it seems my connection was interrupted. What was I discussing when it got interrupted? I don't know. You remember when I got disconnected? What was I discussing?
So after
Hello?
pre-activation.
Okay, pre-activation. All right. So I got disconnected after that. So do you think that we shall continue or we should stop? It's already 148, 150 approximately now. So shall we continue in the next class, remaining part? What do you say? Or at least let me complete this slide. Okay. Thus,
Okay, sir.
ice crystals from upper level clouds that evaporate before reaching the
You
ground.
are not presenting, sir.
Oh, you said something? Somebody said something?
We can't see your presentation, sir.
Oh, you can't see my. Okay, okay. So the presentation I have to again share. Share the presentation again. Your entire screen. Okay. But am I audible and visible?
Yes, sir.
Now can you see the slides? Is my slide visible now?
Yes, sir.
Okay. Yeah. So I was trying to explain earlier before the interruption that from the top of the cumulonimbus cloud now, which has got anvil and which is at a very low temperature, mostly ice crystals are present in that anvil. And once those ice crystals start falling down, now they encounter warmer temperature in the outside air, outside the cloud. And so the ice crystals can get evaporated. Okay. But the ice crystals have ice nuclei within themselves, right? And so, therefore, once they get evaporated, they eject or they leave behind the ice nuclei, which can further act for the freezing or formation of the ice crystals uh, from the water vapor which are present in the surrounding clouds. Okay, thus the ice crystals from upper level clouds that evaporate before reaching the ground may leave behind pre-activated ice nuclei. Okay, because already ice was there on the surface of that nuclei, which fell down from the anvil of the cumulonimbus cloud. Okay, worldwide measurements of ice nucleus concentration as a function of the temperature indicate that concentrations of ice nuclei tend to be higher in the northern than in the southern hemisphere. I mean, this is based upon the global measurements. Okay, and the observations show that the concentration of the ice nuclei tend to be higher in the northern hemisphere than compared to the southern hemisphere. One reason for that could be that in the southern hemisphere we have got mostly the ocean, whereas in the northern hemisphere we have got more land areas. Okay. It should be noted, however, that ice nucleus concentrations can sometimes vary by several orders of magnitude over several hours. I mean, that means I got also a fluctuation or a variation with time. Okay. On the average, the number n of ice nuclei per liter of the air active at temperature T tends to follow the empirical relationship given by this expression log of n is equal to a times T1 minus T. Okay, where n is the number concentration, okay, of the ice particles. T1 is the temperature at which one ice nucleus per liter is active. At least one ice nucleus per liter is active, typically about minus 20 degrees centigrade. And A is empirical constant, which varies from about 0.3 to 0.8. Okay, for A equal to 0.6 in this equation, it predicts that the concentration of ice nuclei increases by about a factor of 10 for every 4 degrees centigrade decrease in the temperature. Okay, for every 4 degree decrease in temperature, the ice nuclei increases by a factor of about 10. Okay, from as obtained from this equation, which gives us the relationship between the number concentration versus the temperature. Okay, in urban air, the total concentration of aerosol is on the order of 10 to the power 8 per liter. Urban airs are generally polluted, so the concentration of aerosol typically has got 10 to the power 8 per liter, and only about one particle in 10 to the power 8 acts as an ice nuclei at minus 20 degrees centigrade. Just see, out of 10 to the power 8 nuclei per liter of air, okay, only one particle can can act as an ice nuclei at minus 20 degrees centigrade. Okay, so this is about the ice, different types of ice nuclei. Okay, and how they act for the freezing of the supercooled water droplets, and also for the deposition or depositional growth of the ice particles within the cold clouds. Okay, the next topic is concentrations of the ice particles in clouds and ice multiplications, how the ice multiply and the large number of or large quantity of ice crystals form. Okay, but we shall stop here today. It's almost 2 o'clock and continue tomorrow. All right, is that okay?
Yes, sir.
All right, so for today I see that we have got 8 students. Okay, good, at least we have more number today than compared to yesterday. So I'm going to stop the sharing. Stop sharing. Okay, I'm also going to stop recording. All right, so in today's